Hello and welcome back to Differential Equations. We are starting chapter 7 on Laplace transforms. We are going a little bit out of the order now because we need to make sure that these two very important chapters, 7 and 8, are covered. So we have to go through at least 7 different sections here. Some are short, some are long, to set your stage for your later coursework in engineering. So a lot of courses like thermodynamics and various chemical engineering courses, electrical engineering courses, will have a lot of Laplace in them because it is a very, very interesting way to solve differential equations. You see, when you write a differential equation, let's say dy dx plus 6y equals to e to the x, for instance, right? When you write a differential equation like this, you say, oh, okay, what are the methods that I've learned, right? I have exact equations, I have integrating factor, I have separation of variables, I have whatever else we had, right? So all of these methods, and hopefully, one of them would work. But then all of those methods had calculus in them. You had integration and maybe even more derivatives and a whole bunch of like that. Integrating factor had the product rule formula backwards. So it's a lot of calculus. Now, what if we can figure out a method that will not include any calculus in it? What if there is a method that converts this differential equation into algebraic equation, right? The stuff that you are used before. What if I could turn this equation into something like 3x plus 6 equals 5, and then you solve that, right? So I mean, this is not equivalent in any way, shape, or form. I'm just saying, like, there is some kind of basic equation. So I'm just going to say, what if we can convert? Now, the real word is transform. And I'll explain why and how. If we can transform this into some kind of algebraic equation. Now, you can solve algebraic equations easily, right? You add, subtract numbers, divide by numbers, move things left and right, you're done. So if we are able to somehow convert this, then our problems in differential equations become basic algebra equations, which obviously by now, after years of taking math courses, you should be able to solve algebraic equations fairly quickly and easily. Now, we have application problems, right, with the second derivative for our spring mass problem, for our currents, right, in electrical circuits. We can do those mixture problems. So there are a lot of applications that population. Sorry, I forgot about that. Population. Then we have kinematics with velocity and all of that stuff. So a lot of applications that we already did in this class, and each one of those can turn to Laplace. So now this Laplace transform chapter becomes this focus, because all of a sudden, hey, you're telling me that I can forget every single method I learned before because I can do Laplace instead and not even do any calculus along the way? And I go, well, yeah, yes, right? Now, Laplace doesn't come also with a free lunch. I mean, you have to learn a lot of formulas and conversions. You have to have your table of transformations with you and so on. Because if you don't have the table, you'll see what happens if you don't have a table. Like, it becomes worse than the problem you actually had. So the trick is that under certain circumstances, your Laplace transform is going to give you much easier problem to solve. But if those circumstances are not met, meaning you don't have the transformation table, which is distributed for students during the exam, so it's not cheating if you are using the table during the exam. In our case, final exam has Laplace on it, at least 4 problems. So you will be using the table, and the table of the Laplace transform is given to you in the cover of the textbook. You can also find them online. You just type in Laplace transforms in Google or Bing, whichever one you like better, and it will get you to the Laplace transforms tables. Now you will use those to solve problems. But let's first see, what is this all about? What is the Laplace transform all about? Well, a Laplace transform is going to take your function or your derivatives and stuff and transform them into a different domain where your equations and functions become different. And they become enough different that they actually eliminate calculus, which is interesting. Now, before we do any of those transformations and see what that means, we are going to define the Laplace transform. All right, so given function f of t defined for all t larger than 0 or equal, right? The Laplace transform of f of t is f of s, which is this way. F of s is, now this is Laplace, it looks like alpha. I like, for years I do this, right? And then people are confused and they say, well, that's not capital L. Then I turn to this. People say that's still not capital L. Then I put like this, and everyone is happy for that to be capital L. But then some people say that's alpha. So I really can't win with any of the notations that I'm using as a script capital L. So you will generally see me do this as a notation, but whatever way you want to write a script capital L. So you can't use this. That's a capital L print. You need a script capital L because this is transformation. All right, so Laplace transform of f of t is given by this integral. Now you are going to hopefully recognize the integral, the parts of this integral from Calc 2. Now, there is a lot of things that we have to unwrap, and literally everything is Calc 2 in this case. So first of all, the type of the integral is improper integral, because we have the integral that goes like this. That's improper integral type 1. That's what it is. So type 1 improper integral, which you learned in Calc 2. And the way to solve that integral, if you remember, you are replacing it with the limit as b goes to infinity, and then you have 0 to b, blah, blah, blah. So that's one section of Calc 2. Then another aspect of this integral that it's also Calc 2 is the fact that this is over here integration by parts. So you have this aspect now of e to the minus st times f of t. Well, that part is integration by parts. So if you don't know that one, if you don't remember that one, right, there is another issue, right, that you have to resolve. Now, luckily, right, luckily, when you are doing Laplace problems, you actually don't have to use this, because that table of Laplace transforms is given, so you can bypass this calculation by hand. However, there will be one question on your final exam where you have to solve this problem by hand to prove the formula from the chart, right, is correct. And that's exactly where I am going to start this chapter at. We are going to say that we can convert, right, one of our formulas, or maybe I can do, let's do two of them, right? Let's do two of them. Now look what's happening here, right? You have some function f of t that you plug into, come on, there we go. You have some function f of t that you plug into this integral, and then when you do all of these calc2 calculations and everything, out it comes a function in respect to s. So this is what the transformation part is. You are transforming t domain into s domain. So when you change the domain, it's transformation. You see, derivatives and integrals are not transformations, because you start with x, you end with x, right? Derivative of x squared is 2x. You didn't transform anything, right? Because you started with a domain that has x's and you ended with a domain having x's. Now, you changed the function from x squared to 2x, which is what we call the operator, right? So operations, right, between two numbers change numbers. Then operators, like integrals and derivatives, change functions. Transformations change space in a sense, because your input space was, in this case, t, time domain, let's say, and your output space is s, which is actually, we'll see, frequency domain. So transformations are even more involved than what your derivatives and integrals are, because, as I said, integrals and derivatives do not change your domains, they only change the function. Now this one changes the function and it changes the domain as well. So transformations, they're much higher creatures, right, than integration and so on. Now integral is used in this transformation, but you see that you are integrating t out, because these 0 and infinity, they apply to t because it's dt. So all of the t's will be integrated out, leaving only variable s behind, which is what switches the domain from t to s. All right, so let's take a look at the way this formula works and prove at least two of these from the page in the back. I mean, in the front of the book. So what would, let's say, what would t cubed or t squared, let's go with t squared. So if f of t is equal to t squared, what would that transform into with the Laplace transform? Well, let's say we don't know, right, the table. We don't have the table available, so you just have to compute it the long way. Well, you would say, okay, Laplace transform of t squared is equal to the integral 0 to infinity e to the negative st times t squared dt. And this is pure calculus 2 integral. All right, we have to write that limit b goes to infinity integral 0 to b. And we like to put this t squared first and then e to the negative st second. That's usually the way we wrote these integrals back in Calc 2, right? So now we use our integration by parts. I believe that's 8.2 in your Calc textbook if you still have it. And you know that you're supposed to come up with a u, in this case t squared, and a dv, e to the negative st dt, and then du will be 2t dt, and the v would be e to the negative st divided by negative s. And then you have the formula, right? The integration by parts, where you multiply u times v and then minus integral v times u. I like to put that arrow there. So what do we have? It's going to be a long line. Limit b goes to infinity. Open parenthesis. So now we have t squared e to the negative st over negative s. We'll deal with that algebra. Minus the integral 0 to b. Oh, this needs to be computed 0 to b. And this one is 0 to b integral. And then I have e to the negative st over negative s times 2t dt, right? So all of that has this limit applied to it. So now, when you simplify this and write it, it's a lot of mess, right? You simplify this and you write this as t squared e to the negative st divided by negative s from 0 to b. The negative can change this into a positive. You can kick 2 outside, and you have your integral 0 to b, or you can kick out 2 over s, because there we go. And you have your t times e to the negative st dt in there. Now, as every semester, right, be very careful what is an s and what is a 5, right? If you can write the 5 to be as square as possible and s as curvy as possible, right? Just don't put this to be 2/5, because it's not. It's 2 over s. And I don't get to change that s into any other variable, because it's s in every single piece of literature I have ever seen. So the fact that you would like me to use, let's say, a y or something that's not going to be confused with anything else, like m, I can't, because it is s, and it's just be careful with 5s and s's. Just like you have to be careful with 2z, but you can cross z. You can't really cross s and make sure it's s. So that's a problem. Anyway, going back to the problem, so this is 2 over s. 2 over s. This is also s over here. So yeah, good luck with that. Now, I see another by parts, so we have to do it again. U equals t, dv equals e to the negative st dt, du is just dt, and v is again e to the negative st over negative s. And we still have the same formula. So now all of this equals 2. We have the limit, b goes to infinity. We have our t squared e to the negative st over negative s, computed from 0 to b, plus 2 over s, open parenthesis, and now I have t times e to the negative st over negative s, minus and minus make a plus, integral, oh, this is computed 0 to b, integral 0 to b, and we have e to the negative st over negative s dt. Finally, we can integrate. A lot of mess, but this is a nested integration by parts, because, right, you had to do it twice. And again, I mean, this is technically something that every Calc 2 student should be able to do, let's say on a final. So I have limit b goes to infinity. We have t squared e to the negative st over negative s. Now I'm going to put this term as well. So it's going to be minus 2t e to the negative st over s squared. Now this minus and this plus gave us a minus here. So that's why I don't have it. So you just have s times s squared on the bottom. And now both of those need to be computed 0 to b. And finally I have minus 1 over s integral 0 to b of e to the negative st dt, which is a basic integral. So we have limit b goes to infinity, t squared e to the negative st over negative s minus 2t e to the negative st over s squared, computed from 0 to... No, I don't need that because I'm going out now with this one. 1 over s e to the negative st over negative s when you integrate. Everything computed from 0 to b. All I need to do is to simplify this term, and we can take the limit finally. So t squared e to the negative st over negative s minus 2t e to the negative st over s squared and plus e to the negative st over s squared from 0 to b. Like imagine without the table of of these Laplace transforms doing this every single time, right? Couple of times per problem. Like, yeah, no. So what you have here is the next one is plug in b everywhere and then plug in 0 everywhere. So we have limit b goes to infinity, and now we plug in the b everywhere. So now that's going to be b squared e to the negative bt, negative sb, there we go, divided by negative s minus 2b e to the negative sb divided by s squared plus e to the negative sb, should be writing this as a bs, would be funnier, divided by s squared. Now we have to go and put 0 everywhere. Now 0 is just going to, right, for each one of these t's, it's just going to start killing them all, right? So we have minus from the formula, and the minus from here gives us a plus, but that's going to be a big fat 0, and it's going to be plus another 0, and now over there is just going to be plus 1 over s squared at the end, because when you plug in 0 here, e to the 0 is 1, right? And it's minus 1 over s, minus 1 over s squared. I hope, if I didn't make any mistakes. So limit, oh, no, now we take the limit, right? Okay, so now e to the negative, I did make a mistake somewhere, because I know what the answer has to be. The answer needs to be this, and I'm having this, so I am not happy. I am generally unhappy. I forgot something somewhere. There it is. You see this one? I distributed that one here, but I did not distribute it here. There it is. Sometimes it helps when you know which answer you're looking for. So this needs to be 2s squared, 2s squared, 2s cubed, 2s cubed, and 2s cubed. Okay, now when I fix that through, so I fixed, starting from here, I fixed this term, this term, this term, this term, and the last term on the bottom. If you go back in the YouTube video and slow it down, you will find all of the terms that because I forgot to distribute, right? This has to be distributed to both terms. I distributed only to the first one and did not distribute it to the second one, which created the wrong answer on the bottom. Now, remember, guys, e to the negative x goes to 0 as x goes to infinity. That should be clear from the e to the negative x graph, which looks like this. Right, so e to the negative x is exponential decay, and as you are going to positive infinity, your y value goes to 0, meaning your e to the negative x goes to 0. So as b is going to infinity, I understand that this guy goes to infinity, but this one is going to 0 much faster. If you remember calculus 2 ordering of functions, you learned that in Calc 1, then in Calc 2 again. The first time was mentioned was with the L'Hopital rule. I mean, if you do the L'Hopital rule here, you will find it. So each one of these goes to 0 because of that, right? Each one of those goes to 0, and you are left. Oh, I forgot to distribute the minus somewhere as well because I got negative. It's supposed to be positive. So the answer needs to be 2 over s cubed, which is correct answer. Now I gotta go back and look where my sign ended up being wrong. Welcome to Laplace Transforms. Actually, no, sorry. Welcome to Calculus 2. Welcome back to Calc 2. And yeah, these are the horrors that we have to now work with. This needs to be a plus. Somehow, somewhere, needs to be a plus. And I just hate to change it there so I can move to the next thing, but I would really like to find it. The chances are it's hard to find things. Could be literally anywhere. So that's a plus. Then that turns into a minus in the formula. Oh, I doubled up on a minus here. There we go. I put, because the formula has a minus there, and then I use this minus to make this into a plus, and then I wrote minus again. So there's that extra minus sign. So now when I go back and delete that negative there, then this stays positive. This changes to positive. This changes to negative. This changes to a negative. And this changes to a positive, and there we go. Holy nightmare. So with 2 mistakes on the possibly the second to the cheapest problem you can have, we have finally that f of t equal t squared transforms into f of s equals 2 over s cubed. So now you might say, well, we just made it worse. The answer to that for now is yes. You made it worse. Plus, you went through that horrible calculation to get there. But all of this stuff will always be worse, worse, worse until you hit the time when you are supposed to solve differential equations, in which case this stuff turns a calculus equation, which is differential equation, into algebraic equation, which you can just solve by adding and subtracting numbers. And that is a big deal. Now, what we learn from here is that t squared transforms into this mess. Now, we'll see later what we do with this. And there is also a transformation table which says that if f of t is equal to 1, f of s is equal to 1 over s. If f of t is equal to t, then your f of s in a transformation table is 1 over s squared. We just discovered that t squared is going to give us that f of s is 2 over s cubed. Now, when you go and put all of these into one formula, you get that f of t, being t to some power of n, transforms into f of s is equal to n factorial over s to the n plus 1. So now, if you are not able to read formulas, you are in huge trouble. Because if the question is asking you to transform, or you need it for a problem, t to the 6, well, good luck doing 6 integrations by parts. Because you saw me mess up twice, right? On a single nested, right? We had 2 integration by parts. Here's one, here's the other, right? And I managed to mess up twice. Now I know I messed up because I know what I was going for, because I know by heart these transformations. I don't need a table. So I knew that I was getting the wrong answer, and that's why I had to go back and find where the mistakes were. But imagine you working out t to the 6. That's 6 integrations by parts. That's a lot of negatives you have to worry about. But if you have this formula, you say, oh, okay, n equals to 6, plug it up there. So that's going to be 6 factorial divided by s to the 6 plus 1. Okay, well, that's s to the 7. That's easy. And the 6 factorial is 6 times 5 is 30, times 4 is 120, times 3 is 360, times 2 is 720. Okay, that's not that bad. And you have your transformation. So knowing the formulas, right, the shortcut formulas, it really, really helps. So now, what are other shortcut formulas that we need to know? Here's the easy one. If your f of t is given as e to the at, so e to the 2t, e to the 7t, e to the negative t, whatever, right? The f of s part is going to be 1 over s minus a, this a here, which means, right, so if this is the formula, this over here, come on, tablet, there we go, that's a formula. I mean, these are all individually formulas, but then you can have t to whatever power, which is why we worry about that one, not individual cases. By the way, this is t to the 0, just in case you're not seeing how that fits our calculation there. And yes, those of you who missed somehow in your Calc 1, 0 factorial is 1. So that's the 0 factorial from t to the 0. And if you need explanation on that, I can provide it as well. Why is that there? Anyway, now this formula is very, very easy to verify, because you can simply say, oh, that's integral 0 to infinity of e to the at times e to the negative s t dt, which is the limit b goes to infinity, integral 0 to b, and all you have is e to the a minus s t dt. Now, there is $1 million trick in solving this, and that is to swap the order into s minus a, and that spits out the negative sign. So 0 to b, e negative s minus a t dt. So when you do that, it quickly, I mean, it's a cosmetic change, but it makes calculations so much easier. E to the negative s minus a t over negative s minus a, computed from 0 to b. And that is limit b goes to infinity. You have your e to the negative s minus a b over negative s minus a, and then minus, and this minus would make, this minus will make a plus, and you have over here e to the 0 divided by s minus a, 1 over s minus a, because obviously this part goes to 0, it's e to the negative x. Come on, tablet, you can do it. That part goes to 0, e to the negative b goes to 0, and s minus a is just a number. So that goes to 0, and e to the 0 goes to 1, so 1 over s minus a. So this is a cheap Laplace problem, cheap Laplace transformation, and it's used very, very easily. If you have your function f of t to be e to the, let's say, negative 4t, your f of s is immediately 1 over s plus 4, because your a is negative 4, and you take that and you stick it in there. There you go. So negative, negative is positive, so s plus 4. It's very easy to use it once you have table of these values. Now, there are certain ones that look weird, which you haven't seen before, like this gamma function, which I can talk about as well. You haven't seen gamma function, which is this. By the way, this is how Greeks and people use Cyrillic, like my native language. This is our G, G. So you have capital G, which is just this, right? That's it, and it's used as for gamma function, right? And a gamma function was developed by Riemann in Germany, and he still used the Cyrillic letter for it. He didn't use the capital G of x, right? He used this one. Anyway, going back to our calculations here. There is transformations for sine and cosine, and sine and cosine hyperbolic, which are all parts of this. And then e to the at times cosine kt, which is very important because of those differential equations where your systems, right, die out in time. That they stop oscillations with time. That was the cases with dampening, if you remember. So if you have spring, right, attached to the system, and there is no friction, there is nothing, it's just free to go back and forth, it will do that forever, right? And that was the problem without that c. So you just had mx double prime plus kx equal to 0. And in this case, you get the pure sine or cosine answer, and it just rocks back and forth forever. But if you say, okay, let's have a friction f there, right, which in our case can be turned into like a dashpot or something, then your case is mx squared plus cx prime plus kx equal to 0. So in this case, your oscillation will never die out, but in this case, it does die out. So this one is purely, let's say, cosine omega t, and this one is e to the negative AT cosine omega t. And you can see this term in front is the one that kills the oscillation, because you can show e to the negative t, right? Decay functions squeezing this into 0, so object eventually stops. Now, we discussed all of this stuff back in chapter 3, and now we would like to compute these problems and these differential equations using Laplace. So clearly we should have these forms as well ready in our tables, and we do. Right, so what are the other important ones in the table? So we have all of the polynomials lined up, including the constant 1, which is technically x to the 0. So that's why constants belong in polynomials, right? Because you can write like 6, you can write as 6 times 1, and then that 1 you can write as x to the 0. So you can write your 6 times x to the 0. So it does look like a polynomial, right? It's x to n. So constants belong there, and all of your stuff. So now we also did E, pure E, and now we have all of the trig ones and the hyperbolic ones. Now they are all offshoots of E, because you can write trig and hyperbolics through some type of E formula. But, you know, for our purposes, we're just going to take a look at these. Now, I'm kind of debating not to copy these in here, but I will. So your cosine, so if you have your f of t to be cosine of some constant kt, now that constant is usually your omega, right, for problems, then f of s, which is the Laplace transform, is s over s squared plus k squared. There is no calculation that you need to do here, guys. Your s is your new variable, technically replaces t, and the k is given in your problem. You just square that number and put it there. So if this is cosine 10t, you're just going to have s over s squared plus 100. So you literally just plug in the value and you are done. If your function is sine kt, then that's going to be f of s is equal to k over s squared plus k squared. So that's our next part. Now, cosine hyperbolic and sine hyperbolic are the same formulas, except they have minus in the denominator. So f of t, the cosine hyperbolic kt, is going to give you the same formula, s over s squared, but now minus k squared. And f of t for sine hyperbolic kt is going to give you f of s equals to k over s squared minus k squared. So these are your transformation formulas for these basic ones. And again, these are the questions that you mostly get when you are solving differential equations. Something in terms of either sine and cosine, if it is that kind of behavior. Unfortunately, we haven't done too much of the hyperbolic ones, but in all honesty, the answers that you guys are getting for these problems are either should be trig answers or hyperbolic answers, right? Those are the two types. Now, we did write them all in terms of ease before, but right, like the programs are getting watered down, obviously, because computers can do most of this stuff now, so we don't even need to teach everything. But I'm afraid that the knowledge base is declining, because you might be the generation that is completely oblivious to it, that we only have trig answers and hyperbolic answers. And those E answers that we were writing were actually hyperbolic answers written in an E form instead of hyperbolic form, because you need to show this contrast between hyperbolic functions and trigonometric functions. And in the end, they have the same form. Unfortunately, due to the situation we're in, and schools being closed and all that stuff, I never had the chance to teach that complex variables seminar or whatever you want to call it, where I introduce these things. So those of you later on going into math majors or electrical engineering, you don't go, what the hell is this? Like, I've never seen this before, which unfortunately happens way too often. Because, as I said, our coursework is becoming less and less and less material, right? Watered down from year to year. And we have one more pair, which is the one with the e that I mentioned. So e to the at cosine kt. We don't have this for hyperbolics because we don't need it, and we'll see why later. But we need it for, right, because when this a is like -3, that's the dampening that kills the motion. So f of s is going to be s minus a. That's going to be very interesting when you multiply with this. You learn that is a shift. And you have s minus a squared plus k squared as you expect. And e to the at sine kt is again the same thing. And s minus, oh sorry, not s minus, it's k now. K over s minus a squared plus k squared. Now, there are many more of these, which include derivatives and integrals and linearization, all of these kind of things, which we are actually going to discover as we go section by section. The goal of today is to understand how to transform a function into Laplace domain, right? Into frequency domain. And in doing so, right, changing the function and changing the domain. That's the goal for today. We're not solving any differential equations. I don't think we're even solving differential equations next class for Laplace. Like, I think it's already all the way in 7.3 when we start solving differential equations. Just a lot of this mess that we have to cover first. All right, so now you got all of these formulas. And we can go ahead and maybe prove, let's prove sine. So your typical exam question. Show that f of t equal sine, I don't know, 3t, right, transforms into f of s. We don't even have to use a. We can just put a number there and make it into a problem. Transforms into, so now that's 3's case, so 3 over s squared plus 9. So this is your exam question. You have the answer, right? So you are graded on the steps in between, which is that integration by parts and all of that stuff that is happening in the transformation itself. So you start by 0 to infinity e to the negative st times sine 3t dt. So this is where you start, and now you go and you grind through the entire calculation, right? So you have limit b goes to infinity, 0 to b, and now I have e to the negative st times sine 3t dt. Now, some of you who paid attention in Calc 2, or those of you who took Calc 2 with me, you know that I labeled this problem as the evil problem, right? It has that trick that people tend to forget of moving the term to the other side so you can solve it. And generally that one creates a lot of noise. So let's go and solve it. I need my by parts, so u equals e to the negative st dv equals sine 3t. du is when I differentiate this, I get a negative SE to the negative ST dt. Good. And when I integrate over here, integral of sine is cosine, and then I have to divide that by 3. So we have cosine 3t over 3. There we go. Integration by parts. Hello, calculus 2, right?
Isn't the integral of sine negative cosine?
Yes, it is. Thank you. That would mess things up really badly. Yes, yes, yes. Yes. Derivative of sine is positive cosine. Integral of sine is negative cosine. Very good catch. Actually, I should go by. I knew that. I was just testing you. Yeah, very good. Yes, that minus has to be there. All right, let's go. We have e to the negative st times negative cosine 3t over 3 minus the integral 0 to b. This is computed 0 to b. Minus the integral 0 to b. And then we have this negative, and the formula negative. That's 3 negative signs. So it just stays negative, but I don't have to write these ones. And I get S e negative st times cosine 3t over 3 dt. Now we have to simplify algebra in this one. So what do I have on the first one? I have a negative 1/3 e to the negative st cosine 3t from 0 to b. Minus, and now I'm going to kick s over 3 outside so that I can forget it later and mess up. And have this 0 to b e to the negative st cosine 3t dt. All right. The definition of insanity, right? Doing the same thing over again, expecting a different outcome. That's exactly what we are going to do. Take another integration by parts over here. And the dv cosine of 3t dt du negative se negative st and v integral of cosine is sine. This time I'm going to get it correctly. I'm going to make our differential equations class into a drinking game every time I get something right. Anyway, we have negative 1/3 e to the negative st cosine 3t 0 to b. Now I'm not going to forget to distribute this one. Negative s over 3 times e to the negative st times sine 3t over 3. So that's when you go this way, and that one as well. So there are no negatives other than that one, so that stays like that. Now we have a minus from the formula, and then we have this minus and this minus, so we have 3 minus signs. So minus in the formula, minus here and minus here. So that's 3 minus signs, so it stays negative. And I get to write s over 3, and I get to write e to the negative st, and then sine 3t over 3. And that gets its integral and dt. Good. Let's fix it just one more time so it looks nice and clean. Negative 1/3 e to the negative st cosine 3t. Now minus s over 3 s over 9 e to the negative st sine 3t 0 to b minus s over 9 integral e to the negative st sine 3t dt. All right, so this is where the trick kicks in, because we went through 2 iterations of integration by parts, and we did not eliminate either e or sine, because you can't, right? They don't integrate out like, let's say, polynomial term x to the 4th, right? Because when you take 4 derivatives of x to the 4th, is gone. So first derivative drops down to x cubed, the second derivative drops it down to x squared, third derivative drops it down to single x, fourth derivative drops it down to a constant. The next derivative just deletes it, right? Completely. So we can take 1,000 derivatives of e to the x and it's still going to be some form of e to the x, and 1,000 derivatives of sines and cosines will still give you sines and cosines, because they're looping every 4 calculations. So to solve this problem now, as I said, the $1 million trick here is to realize that the term you have after 2 integration by parts, this term here, is exactly the same, or it's of the kind, of the starting term. And what you do is you move it and add that here, that s over 9 blah 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 dt, they add together on the left, and you have the rest of the stuff that has no integral signs on the right. So again, if you haven't been doing these problems too much in your Calc 2, I understand if you're confused and angry. But here it is, the integral 0 to infinity of e to the negative st sine 3t dt will be added to the s over 9 integral 0 to infinity, this is 0 to b, e to infinity negative st sine 3t dt. As you can see, these 2 integrals are the same, it's just that their front coefficients are going to add. Now you say, but hold on, you had 0 and b, and now you have 0 and infinity back. Well, yeah, because I don't have this limit in front anymore, so I'm just going to plug this infinity back into b and have it 0 to infinity again, just so I can add these 2 integrals. Now, on the right-hand side is all of this that it's a leftover. Negative 1/3 e to the negative st. Oh, I forgot the limit. Holy nightmare. There we go. Limit b goes to infinity. Negative 1/3 e to the negative st cosine 3t minus s over 9 e to the negative st sine 3t from 0 to b. All right, so on the left, when you factor the integral, you are going to get 1 plus s over 9 times the integral that we want to compute. Sine 3t dt. And on the right-hand side, you plug these b's and you try to solve the problem. So you have limit b goes to infinity. That's not going to fit. Probably not going to fit if I start there either. Limit b goes to infinity, because I need to write it 2 times now. Negative 1/3 e to the negative sb, the cosine 3b, minus s over 9 e to the negative sb sine 3b, minus, and now you plug in a 0, and when you plug in 0, this becomes 1, this becomes 1, so it becomes plus 1/3. Well, let's just put e to the 0 cosine 0. It's okay. And plus s over 9 e to the 0 sine 0. It fits somehow. Okay, so let's add these two. So this is, did I forget? I forgot a square. I forgot a square. I know. I know. I see it. I just have to find it. Where is the square that I am missing? I missed a square somewhere. Well, we'll get to it. 1 plus s over 9, 0 to infinity, e to the negative st sine 3t dt is equal to what? Okay, so when b goes to infinity, you all of a sudden have cosine of infinity. The limit for something like that does not exist. However, it's bounded between a -1 and +1, because cosine of any number, don't put infinity. Infinity is not a number. Infinity is a concept. If you put in 1, or you put 10, or you put 101, or 10,137, right? No matter what you put in a cosine, you will always get values that are in between -1 and 1. So sine and cosine in a limit cannot contribute when it goes to infinity, right? They don't contribute at all. So we don't have to worry about them. So when you have this cosine, it's like its cosine is not there. And this one, right, going to infinity makes this term goes to 0. Now, cosine at some point is going to be 0. It sounds -1. Sometimes it's √2/2, whatever it is, right? But the whole term goes to 0 because of that e to the negative sb. Same thing happens here. This puppy goes to 0. So this b can be any value you can possibly want, including infinity, because right, it's undefined at infinity, but still it can't be, like if it is by some miracle to define it, it will still be between -1 and 1, and that's definitely not going to do anything when it's multiplied by the 0 before it, right? So that's going to give us another 0 there. And now this term over here is 1/3, because you have e to the 0 and cosine to the 0, and then plus 0 over here because sine of 0 is 0. And now what I get here is integral 0 to infinity e to the negative st sine 3t is equal to 1/3 divided by 1 plus s over 9. And I know I'm missing a square, because now when I multiply top and bottom by 9, I am getting 3 over s plus 9. And I need to get s squared plus 9. So I did mess up somewhere when I distributed an s somewhere. I forgot to distribute s to get s squared there, just like I did in a previous problem. But we got the question right. I just need to go back and find why is this not a square. I need a square right here, which means that I need a square right here. And where is that square? There is the square. There is an s here, and then there is the s here, and when those two s's multiply, you get s squared. So this s is a squared, this s is squared, and that fixes the problem down the line. So that's an s squared now. That's an s squared right there. That's s squared. That's s squared. And this becomes s squared. And there is your form of k over s squared plus k squared coming from sine k t, where k was 3. Well, 3, 9. Very simple. So this is the reason why we use those tables. These integrals, they're not impossible, but as you can see, it's with so much algebra, so many negative signs, so many distributions, right? If you are to write each step down, and I was skipping step here and there, right? It takes forever to compute, right? And it's not friendly at all, which is why we use the chart. See, we can do the problem in this much, right here. Oh, k is 3. Plug 3, plug 3, 3 over s squared plus 9. Done. None of the work for the integral. And that is what is expected from you on the test, to be able to use the chart so that you can quickly and efficiently convert differential equation into algebraic equation. Because remember, there is also a procedure that we haven't talked about yet, inverse Laplace transform, because now you have to go back. Let's say you have your transform, right? What is the, you have your transform, like what is the original problem? Now, before we move to that, I also have to talk about linearity of this. I'll just put this way, or f of t equals sine 3t goes into the formula k over s squared plus k squared is equal to 3 over s squared plus 3 squared is equal to 3 over s squared plus 9. Just want to make sure that you understand how to use the table. And the table of these Laplace transforms, you either go and print one online, or if you have the textbook, right, and you do have access to textbook in MyMATLAB, it's on the front cover. You just take the hard cover and just flip it open, and the first thing you see, well, on the right page, is table of Laplace transforms. Unless someone you bought, rented, or I mean, you're renting the book, or you bought a used book and someone ripped it out. But if it's a brand new book, it has to be there, the front cover. All right, one more concept before we hit inverse Laplace, and that is a linearity of Laplace. Oops. Come on, pen. So Laplace of AF plus BG, right, those are of T, obviously, is A Laplace of F, of T if you want to write it, plus B Laplace of G of T. I keep writing these, need to be curly. There we go. Now, this technically means that you can, if you have a multiple term to do the Laplace transform, you just do it term-wise. You are not considering the entire function, but each term independently. So let's say you are supposed to do the inverse Laplace of t cubed plus 6t squared minus 4t plus 9. Right? Let's say this is your problem. You will apply Laplace transform to each one individually here. So you're going to say, I need Laplace transform for t cubed plus 6 times Laplace transform of t squared minus 4 times Laplace transform of t plus 9 Laplace transforms of 1. Now you know that the Laplace transform of t to the n is n factorial over s to the n plus 1. That's something that you either memorized or you looked in the chart. So you just go and you immediately work all of these out. Okay, 3, that's a 3 factorial divided by s to the 4 plus 6 times 2 factorial s to the 3 minus 4 times 1 factorial, well, it's just 1, who cares? It's going to be s squared plus 9 times 1 over s. Well, let's write 0 factorial since we wrote the others. I don't want to trigger 0 and then they go and complain. So 6 over s to the 4 plus 12 over s cubed minus 4 over s squared plus 9 over s. There you go. So your Laplace transform of this polynomial in a time domain is this in what we call frequency domain, the Laplace transform. So linearity formula, the one that I wrote up there, right, technically means that each one of these terms are solved independently from any other term that it's solved in this. So if one of these terms was e, one is cosine, it doesn't really matter to us, right? Because we know that we can look at each one of them separately and then just go like that. Oh, time to cry. It's 12:28. We only have 20 minutes of the class and I'm just starting inverse Laplace. All right, well, at least inverse Laplace is going to look at the chart backwards. And you're going to look at 1 over s, right? And you say, oh, that's number 1. You're going to look at 3 over s, and then you also say, well, that's 3. Like, how do we know that? Well, let's talk about inverse Laplace transforms. Here, written in blood. Read the table backwards. So, if f of s is 1 over s, then f of t is 1. If f of s is equal to 1 over s squared, then f of t is equal to t. If f of s is equal to, let's say, k over s squared minus k squared, your f of t is sine hyperbolic kt, because it was a minus in here. So when you when you have these situations, right, you will and you will have that in every problem for differential equations. You have to be equally good with the inverse transforms and the tables, just like as a forward transform. And the reason is, right, that's the algorithm to solve differential equations. You will get your equation as, right, in terms of t. Then you will use Laplace to transform it into s. In that process, you will kill all of the calculus. But when you solve that s equation, it's still the equation in s. And no one cares about that, right? You have to bring it back into the t domain. And that is where inverse Laplace transform kicks in. So you will be doing transform and then inverse transform in every single problem, right? The same thing like you did for u sub, let's say in Calc 1. You used u sub to transform your x integral into a u integral. That's actually a transformation because you change your domain from x domain to u domain, by the way. So when you use the u sub, right, you change your problem from x to u, you make it easy, you integrate in u domain, and then what do? You plug back your transformation in, and you circle the solution that only has x's. Well, the same thing for Laplace transform. Your problem is given as a derivative of t and functions in terms of t. You transform everything in s, you make a joke out of the problem, you solve it, but now it's time to go back and present your solution in terms of t, just like you did for u sub, right, in Calc 1. So now, I mentioned the basic chart says, right, that if your f of s is 1 over s, then your transformation is that f of t is equal to 1. And then I quickly said, if f of s is 3 over s, you are getting that f of t is 3. Well, yeah, because this one you can write as 3 times 1 over s. And that linearity allows you to kick 3 outside of the inverse transform, and then you just do the inverse transform for this and you get 1. So technically, when you transform it, you get 3 times 1, which is 3, and that's the answer. So now we are getting into this big algebraic issue here, which is factoring and breaking fractions apart and all of these kind of things that, you know, for most of the students is holy nightmare. But it just needs to be done, right? It needs to be done. So now we are going to have more details on this, but it's not clear in every problem. And you have to work hard to understand how these things work. For instance, f of s is given as 16 over s squared plus 9. Find inverse Laplace of f of s, because obviously that will give us f of t. See inverse Laplace, this -1. Remember the inverse trig functions, the inverse hyperbolic functions, the blah, 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 inverse f of inverse, right? So inverse Laplace will have clearly that notation to follow literally everything else we have in mathematics. So, what are we going to do here? Well, you go and you find in the chart what is this closest to. And when you look closely, right, at the charts, you will say, well, the one that has k on top and a plus on the bottom. I think that was like a sign. Yeah, that was sign. Okay, great. So if my f of s is k over s squared plus k squared, but now this is 3 squared and this is 4 squared, and that doesn't match. Okay, that's fine, because I can multiply and divide by 3 that I need and completely not use this 16. So this is 16 over 3, and then I have 3 over s squared plus 3 squared. There it is. 16 over 3 sine 3t. Okay, it can be done. But see, these were hoops, right? That we had to jump through to come up with the inverse Laplace. Because you should start and you say, oh yeah, 16, I can take a square root of that, right? But that 4 doesn't match the 3 and I need the 3. Well, fix it, right? Fix it. The same way, let's say you have 4s divided by s squared minus, I don't know, 25. Doesn't really matter. 25. You go, aha, it's a minus, so it's a hyperbolic one. I do have an s on top, which means it has to be the cosine one. I know that I can just ignore the constants. Oh, okay, well that was easy. So all I need to do is to push 4 off of the fraction so that I can have my thing written this way. Okay, that transforms into f of t is equal to 4 cosine hyperbolic 5t. Done deal. Right, so being able to kind of grind through this constant, right? You see that there is, oh, I have a constant that it's in my way. Just kick it off, right? And we did that, right? We kicked this 16 off, but we had to multiply by 3 because we didn't have it. Now, if 16 was 15, I could break 16 into 3 times 5 and then use a 3 for transformation and kick the 5 off. Right? There are a lot of things that you can do. But none of those, right, when you are just trying to fudge a constant, stand anywhere close, right, to the big problems that we might run into, which we are going to meet in 7.3. So I'm not going to go into those. I will mention them because I did promise that I will give you the list of things at the end of the lecture, of the things that you should ruin your Thanksgiving with, so that the rest of the chapter and then chapter 8 is a joke. So obviously, let's call it the list for chapter 7 plus 8. That's not chapter 15, it's 7 and 8. We already seen this. Number 1, improper integrals. Taking everything else, everything here, guys, is in your calc too. So improper integrals. If you don't know how to change that into that limit and change infinity into b and grind through the limit all the way to the end, like you can't solve any of those basic Laplace transformations. Number 2, integration by parts. Number 3, hello to partial fraction decomposition. So partial fraction decomposition, this is what you need for your inverse Laplace, right there. And that's your entire 7.3 insane amount of partial fraction decomposition. If you don't remember that, if you are slow with it, like you know it, but you're slow, it's not gonna cut it, right? You have to be quick with partial fraction decomposition, and that's your inverse. That's your inverse Laplace right there. You will need also L'Hopital's rule. That's Calc 1. Because some of the limits, right, you have to use L'Hopital's rule to solve. There was no other way. And very limited amount of trig identities. Like I can list them all. They might or might not come up, but it's better to be prepared if they do. Trig, and I'm just going to say sine squared x plus cosine squared x equals 1. Sine 2x is 2 sine x cosine x. Cosine 2x is equal to cosine squared x minus sine squared x, and the power reducing. These are the 5 formulas just in case, right? So this is 1 minus cosine 2x over 2, and cosine squared x is 1 plus cosine 2x over 2. So these are your 5 trig formulas. Again, you might not encounter them. It depends on what is on the homework, but they can really help and simplify the problems, especially for like the transform, where you have multiple problems. Multiple functions, and you have, let's say, sine times cosine. Well, I'm just going to give you immediately where, like, let's say this one can be very, very useful. See, if it says f of t is equal to, let's say, 5 sine 3t cosine 3t. Let's say that's, and it says transform this. Now, is this a question because someone wants to torture you? No, guys, this models some kind of oscillating behavior. And sorry, if you are mechanical engineer or you're electrical engineer, like this is the stuff you're looking at, because you have springs and you have inductors and capacitors. Like this is the type of functions that periodic functions are the types of functions that you're dealing with. So it is not like evil math people came up with these things just to annoy us, right? No, you picked the major which has this as its basic idea, right? And that's the mathematical function which models it. So let's go. Now you say, oh, I have multiplication of these two, right? So now what are the cunning student would say like this? 5. Now I need 2 sine 3t cosine 3t, but if I multiply out of nowhere by 2, I have to divide, right, to kind of balance it off. And then this becomes 5/2 sine 6t, because it just doubles the angle. That's exactly the formula. So now when you have this situation, all of a sudden it's, oh, my k, right? Oh, poor k, k is 6, right? And you immediately writing your transformation, right? You didn't have to go through that integral and that insanity for like 30 minutes, right? And I messed up both of them. You saw me mess up both of them, right? Because it's just way too many distributions and minus signs, and I'm trying to rush so I can actually talk about everything that is supposed to be in this class and not just work out those 2 examples, for 2 hours. So now we have your 5/2 constant, and you have your, it's sine, right? Sine puts k on the top, which is a 6, and then s squared, it's a sine, so it's a plus, and this is a 36 right there. And then you go, woo, right? We're done. Now you can cancel, right? You can cancel your 6 and a 2 now, right? And make this into 15 over s squared plus 36. Right? When you cancel the algebra. So we went through something that looked terrible, right? And just imagine trying to do this in that integral, where you have this thing, and yeah, good luck doing integration by parts twice. where your one function is e to the negative st and the other function is sine 3t times cosine 3t, right? No matter whether you pick that function as a u or dv, you have problems. Because if you pick it as u, you have to use product rule, and if you pick it as dv, you have to use u sub. so it's absolute nightmare. But see, a simple trig identity, right, transforms that problem into something compact where you can use the chart right away and be done. So 7.3 will be completely devoted to inverse Laplace transforms, because now 7.2, which is our next class, is going to set up stage for differential equations and how to convert differential equations. So we need to talk about Laplace transform of the first and second derivative and all of that stuff. And we're going to put some things in perspective there, but it's not really all the way until 7.4, well 7.3 actually, but also 7.4, when all of this kind of clicks together. So be patient. This was a lot of mess today to compute these things. Hopefully you understand that you will be using chart to complete problems, but then if you're going to trip on some of these trig identities, then that's going to be a problem, right? Because you saw what happens with the integral. So I'm hoping that your Thanksgiving, and we're going to mention this on Monday again, and I'll try to have that if anyone shows up on Tuesday evening. I'll try to have before Thanksgiving, right? If anyone shows up to that, we can have this virtual kind of class where you guys are going to ask questions, and I'm going to put some problems down so you can refresh and review these Calc 2 concepts, because we're going to do 7.3 after Thanksgiving. So you will have actually chance to review all of this stuff prior to us having the partial fraction decomposition worked out inside the inverse Laplace. And yeah, that's that. Questions, concerns, anything? Or are you completely speechless? I guess there will be a negative, huh? All right, let's say bye to